What happens when we dissolve a compound in water? Well, the answer depends on the type of compound. Remember, we have two types of compounds: ionic compounds. Remember, ionic compounds always have a metal, at least a metal in them, or covalent compounds. Covalent compounds do not have any metal in them. Now, let us begin with ionic compounds. If you dissolve an ionic compound in water, for example, sodium chloride, which is also called table salt, what actually happens? The very first thing we need to understand is that although sodium chloride is written as NaCl, it is not really NaCl. It is actually sodium ion and chloride ion. The reason is this: anytime a metal reacts with a non-metal, the only relationship between them is that electrons will be transferred from the metal to the non-metal, which means that the metal will become a cation and the non-metal will become an anion. So anytime you see an ionic compound, always understand that the metal in the compound has a charge. It may not be shown. The non-metal or the polyatomic ion in the compound also has its own charge. Let us take a look at another example. Magnesium nitrate. This is also an ionic compound, and again, we are not showing the charges, but the charges are always present there. Magnesium is from group 2A, so it will always carry a charge of +2 when it is combined with a non-metal. On the other hand, nitrate is always -1 because it is a polyatomic ion. Now, if we have an ionic compound and we dissolve it in water, for example, sodium chloride, which, as we already know, has these charges, if we dissolve it in water, it will dissociate into the ions. It will break apart into the ions. Now, to indicate that this is occurring inside water, we will place AQ as the subscript on all of them. This is what is happening in water, and I will show you why it is the way it is written. Covalent compounds, on the other hand, when you dissolve them in water, they do not dissociate. Let us take a look at an example. Glucose. It is a covalent compound because there are no metals in it, which means there are no transfer of electrons. If you put glucose in water, it will dissolve, but it will not dissociate. It will remain as a unit. Then the next question is this: how do we know that a compound will dissociate in water? This is how to test that an ionic compound will give ions when you dissolve it in water. Take a look at this simple experiment. If you have a glass of water and you put some water inside the cup. And you insert two metals, let's say two copper wires, in the cup. And you connect one end of the copper wire to a light bulb, and you connect the other end to a battery, and the battery to the light bulb. You will see that there will be no light because water is a poor conductor of electricity. If you now add some table salt into the pure water, add some sodium chloride, you will see that the lights will glow. Because the solution is now an electrolyte solution, which means it is capable of conducting electricity. And why is it capable of conducting electricity? Because it contains ions that will be able to propagate the electrons, which leads to current that is lighting up the bulb. Now, instead of using the sodium chloride, if you add the glucose into the water, no matter how much glucose you add into the water, you will see that the light bulb will not light up. The reason is because a glucose solution is not an electrolyte solution because it contains no ions. There are two types of electrolytes. There are those that we call strong electrolytes. And they are called strong electrolytes because the compounds dissociate completely in aqueous solution. For example, if you dissolve aluminum chloride in water, it will dissociate completely to form aluminum ions and chloride ions, leaving nothing behind, which means all of the AlCl3 will be converted into the aluminum ions and the chloride ions. On the other hand, there are those that are called weak electrolytes, and they are called weak because the compounds do not completely dissociate in aqueous solutions. They leave some of the compounds behind intact. Example is hydrofluoric acid. If you dissolve this in water, it will not dissolve completely. It will give you some ions, but not all the compounds will get completely converted into the ions. And one way you can easily tell is the presence of the reversible sign. The reversible sign is telling you that the original compound is not completely going to the ions. Non-electrolytes, on the other hand, just would not give ions in solutions. They can dissolve, but they would not give ions. An example again is the gasoline you put in your car, or the glucose solution that we mentioned earlier. Substances that refuse to dissolve in aqueous solutions are said to be insoluble, and we can predict whether a compound will be soluble or not using what is called the solubility rules. So solubility rules can be used to predict whether a substance will be soluble or not. Let us now learn about the solubility rules. The first rule is that all compounds of lithium ions, sodium ions, potassium ions, rubidium ions, and ammonium ions are always soluble. What does that mean? It means anytime you see lithium ion or sodium ions or potassium ions or rubidium ions or ammonium ions in any compound, then that compound will definitely be soluble. That is why the word always is used here. Now, if you look at all of these ions properly, something that is common to them is that in the periodic table, they are all from group 1A, except for the ammonium, which is a polyatomic ion. So whenever you see any of these 5 ions in a compound, then the compound will be soluble. But all of these ions are positively charged. What about negatively charged ions that are always soluble? So, rule number 2. All compounds of nitrate ions, acetate ions, and perchlorate ions are always soluble. What that means is that anytime you see nitrate, acetate, this is called acetate, and at times it is written as C2H3O2 minus. They mean the same thing. Or perchlorate ions. Anytime you see them in a compound, you can simply assume that the compound will be soluble. That is why the word always is used here. Now, let us take a look at some of the gray areas. Rule number 3. Compounds of lead-2 ions, silver ions, and mercury-1 ions are usually insoluble except when they are combined with the ions from rule 2 above. Let me explain. Compounds of lead-2 ions will be insoluble except if it is lead combined with nitrate, that will be soluble. Or if it is lead combined with acetate, or if it is lead combined with perchlorate. Also, silver nitrate, silver acetate, and silver perchlorate will be soluble. But all the other compounds of silver, we can assume that they are not soluble. And mercury 1 nitrate, mercury 1 acetate, and mercury 1 perchlorate will be soluble. Any other mercury 1 compound, we will assume that they are insoluble because they definitely are not soluble. That is rule number 3. Let us now move on to rule number 4. Compounds of chloride ions, bromide ions, iodide ions are usually, and the key word here is the word usually, soluble except when they are combined with ions from rule number 3 above. Now, what does this mean? Anytime you see chlorine, bromine, or iodine in a compound, you should assume the compound is soluble, except when they are combined with lead, or silver, or mercury 1. For example, lead-2 chloride is not soluble. Lead-2 iodide is not soluble. Also, silver chloride is not soluble. Silver bromide, silver iodide are not soluble compounds. So are mercury 1 chloride, mercury 1 bromide, and mercury 1 iodide. So anytime you see chlorine, bromine, or iodine, we can simply conclude that they are soluble except the 3 ions that are in rule 3 above. Let us move on to rule number 5. Compounds of sulfate ions are usually soluble except when combined with barium ion, strontium, lead, silver, mercury 1, and calcium. These 6 ions, when they are combined with sulfate ions, are not going to form a soluble compound. So what does that mean? Calcium sulfate is not soluble. Barium sulfate is not soluble. Strontium sulfate is not soluble. lead 2 sulfate, silver sulfate, mercury 1 sulfate, all these 6 sulfates will be insoluble. Rule number 6. Hydroxide ions, phosphate ions, sulfide ions, carbonate ions, and other ions will form insoluble compounds, except when they are combined with ions from rule number 1 above. What does that mean? Let us first take a look at what we have in rule number 1. We have the lithium ions, sodium ions, potassium ions, rubidium ions, and ammonium ions. So that means that these ions will only be soluble when they are combined with those positively charged ions in rule number 1 that are always soluble. For example, lithium hydroxide, lithium phosphate, lithium carbonate will be soluble. So will potassium hydroxide, potassium phosphate, and so on.